factor? And maybe we can cancel something.
Factor out a secant from the top.
Amber, that was a good eye. She goes factor out a secant of x in the top, right? And if you did that, oh my goodness, what comes out? That becomes secant of x. That's a plus. What's this?
10.
Does anything cancel?
Yeah, for the numerator, denominator.
Don't you love natural log and trig functions? Well, these are the identical. Woo! Woo! What's third? Now I do want to point out something. Remember I was talking about antiderivatives? One of the craziest things is students have to eventually, at one point, calc 2, find that antiderivative.
Isn't it?
And it's not an easy problem. You got to kind of manipulate and stuff. But if you can remember, that means that this is the derivative of this.
Mm-hmm.
That means the antiderivative of this will be what?
Natural.
That's what the answer will be. Everyone follow me? Okay. If that's the derivative of this, then the antiderivative of this is you going backwards. But that's a tough one in Calc 2. So I'll ask students, anyone remember doing this one? They're like, no. All right, everyone, you know we're almost done with 3.6? And we'll talk about 3.7 today because it's fun. Before we do, there's one more goofy type of problem. We have yet to see something like this yet. Look at this game. This is fun. Come on, we haven't seen this yet. Y equals what?
X to the power x.
X to the x? We've seen x squared, we've seen e to the x, we have not seen what? Exponent x. So it requires a special type of differentiation. You go, what is it, implicit differentiation? Well,
Yeah.
it's more of called logarithmic differentiation. So if you want to put that in your notes, you can. To solve y equals x to the x power, and you want to differentiate it, it requires a specific type. We call it logarithmic differentiation. Wait, that didn't have a log in it. I don't care, it's kind of goofy, right? The base has an x and the exponent has a what? X. So it requires a special type. It's going to be called logarithmic differentiation. So you know what step 1 is? Because it's so goofy? We actually are not going to e both sides like in that math proof. Our first step, we're going to take the natural log of both sides. Only do that for what kind of problem? This kind of problem. X to an x, I'll give you another example. X to the sine of x, if you want me to work that problem. So, first step, do what?
Take natural log both sides.
Because if not, we had nowhere to go. We couldn't go anywhere. So we start out like that. Everyone see that?
Mm-hmm.
Now don't forget we did that. We wrote out on a y on a y. We'll come back in the end of that.
Does y become the exponent or something?
Oh, she's on to something good. Hey, before I finish this up, does anybody remember what ED on a blah was? What's ED? I don't even know how you spell blah.
L-A-T?
B-L-A-H? Is that right?
Uh-huh.
So, or what's ED on a blah then?
Blah.
So what's ED on of x? X. What's ED on of y?
Y.
Y, right? Everyone agree?
Doesn't
All right.
that become x natural log x?
Uh-huh.
Oh, good eye. All right, Stephen. So when I took it on both sides for this special case, he goes, you know what? Yeah, you're allowed to move that power in here. It's a property of logs. And you definitely want to do that. So I'm going to bring that dude down now. Now all we have to do is implicit differentiation. Woohoo! Seriously. That's all we're going to do is implicit differentiation. I'm serious. That's all we'll do. But what rule do you need on the right? Please spot it.
Product.
Product rule. You need product rule on the right. But we'll just do implicit differentiation. Differentiate both sides with respect to x. If we differentiate Amber anything with a y in it, right next to it we'll write dy dx. Okay? So I say we start with this side. It's going to be quick. What's the derivative of x? 1 over x. So what's the derivative of this?
1 over y.
1 over y.
dy dx.
And then Josephine, I'm differentiating implicitly because I differentiate something with a y in it. Right next to it I write dy dx.
Now why'd you put the y on the bottom?
Oh, look. Do you follow? That's exactly right. We just had another variable. That's how chain rule works. That could have been like a G. Amber, this could have been like ln of g.
Then it'd
I
be
would have
1
said
over g.
1 over g and then d what? dg dx. It just happens to be what letter every time? A y. So you're like, oh, okay. What if it was a q? What would it be? 1 over q times what?
DQ.
dq dx. Or even better, what if it was what if this was ln of t? 1 over t times what?
DT over DX.
There you go. But everyone, I'll go back. What was this? It was a y, so I'll say 1 over y times,
dy dx.
and our goal is to find dy dx, so we're going somewhere.
Mhm.
But everyone, you do need product rule there.
So x.
There's m, there's n.
Yeah.
First,
X 1
what's
over
the derivative of the second?
1 over y dy dx.
Yep, ln of x, derivative is 1 over x, Amber, good. Do you agree? So first, derivative of second. If you need to, you can label these. But I know we just learned product rule a few days ago, so you can label this. Josephine?
Why the product rule of x isn't a constant?
When x, that right there is a variable, right? If that was a constant, we would not have to do product rule. But we have to do product rule because we had a function x times another function, natural log of x. The key is the variables. We got a variable times a function of the same variable. I know, but if that was just like a 3, Josephine, 3 on a max, we don't need it. Because the constant rule, we just leave the 3 in front, right? But Josephine, I do want to point out, these come up a lot. Things like this in calculus. X ln of x, you need product rule. X e to the x, you need product rule. X cosine of x, you need product rule. And there, you can just imagine how many times I've graded calc tests, and that's where students made errors. They missed product rule. It's because it's a variable there. So what I'm going to do, m times m prime plus n times m prime.
So it's gonna be x times
1 over x, good, plus
ln x
ln x, I'll put a parentheses around it,
times 1.
times a 1. Now all you gotta do is get dy dx by itself, you're done.
One second, professor.
What's that?
Oh, sorry, that side is x, not y. Sorry, x, no, okay, I got it wrong, sorry.
Oh, okay.
Hold on a second.
Hey, anything you want to simplify on the right side though?
You can
Do you see anything, Josephine, I can simplify that right? Now that I did the product rule? X times a 1 over x will just be a 1. So let me rewrite this. 1 over y, dy dx, equals 1 plus natural log of x. Right? Now the only thing I gotta do is isolate dy dx. That's it. That's all I have to do.
Can you substitute 1 over x for 1 over?
Yeah, you can do 1 over y.
Can't do that.
One
There's
over
something
x.
else we want to
Just
do.
multiply.
For this last step here, Kelly, I do
Times.
want to get this by itself.
Times
So I need this
y.
1 over y off here. So I have to multiply a y on both sides?
Yeah.
Amber, great idea. So I'm going to write that. But, I'll be honest with you. Everyone, here I go. I'm going to multiply a y, so I have to put a parentheses around this what? Did everyone see this?
Oh, then you have to put the original value of y over there, right?
There you go. So here's what I'm going to tell you. If you check the back of the book, great job on this, you will not see this. Because the author desired, and I think you'd want to too, is write this answer all in terms of x. So look back in your work. Look all the way back up here. Is there something I can put in place of that other letter y? Look all the way, go to the beginning.
X to the x.
Let's do it. Everyone okay if I put that here?
Uh-huh.
So let me write it. X to the x. That's what you'll see in the back of the book. I call back
Are
of
you
book.
gonna write it on the test that you want it in terms of x or in terms of y?
Nah, I would accept that. Well, hey, what if I did a multiple choice on the final? I would put it like that. Hey, this is what I encourage you to do. When you don't have to do 1,000 of these, but would you try this guy, the one I think I put it for homework problem? Don't do it now, but would you try it like tonight? What was that? And would you just try it? It would be very what? Very similar. Would anyone try that one?
Mhm.
But you do need what? Logarithmic differentiation. Watch, we'll try it now. Isn't that funny? X to an x. Just, if you can remember that, how do you differentiate it? Y equals x to the x. Logarithmic differentiation. Take the log of both sides in the first step. Cool? Sarah, did you like it? Should I put that on a test or no? No. She goes, no. She goes, don't put those. But I can do ln of a trig function, right? All right. ln of secant, ln of secant plus tan, ln of cosine, ln cosecant. No, I won't do it on the coseking, because then you Bellraz, we'd have no derivative cosecant. I know you all know these derivatives, but you don't see that as often.
Who came up with this, Euler or Leibniz?
Oh, good question. I'm gonna say Euler. But they both kind of hit, sometimes they hit things hard at the same time.
Gotcha.
Those are some smart guys. This guy's like the smartest in the world ever. For math. I'm gonna forget another one of these one day. Well, another one of these guys come one day.
What about Tau? Terence
And
Tau?
people, when they just couldn't solve problems back in the day, they go to him. He'd be like, give me a second. He had the answer like 2 days later. You know? Did you ever see the bridge problem? Where you're like, we're trying to figure out a way to cross all these bridges, but we want to go to a bridge once. They went to him, it involved mathematics, and he comes back and he goes, it's impossible. That's his answer. And he had all this graph theory. All this graph theory. So when I teach the lowest level credit course here at it's a credit course at Anne Arundel, it's called Math 100. But in that course, we do Euler circuits. It's fun. We figure out paths, like the quickest path to take, and things like that. It's fun. They're called Euler, named after him. All right, well, the last thing we're doing today is 3.7. We'll do a couple of these. EVA, what's the derivative of position? Velocity. What's the velocity? Acceleration, right? Someone agree? Rate of change of position with respect to time, we call that velocity. Rate of change of velocity with respect to time, what do we call that? Acceleration. Everyone agree? So I'm just going to put PVA up here. Because if this was like a y, then what would this be? Y what? Y prime, what would this guy be? Y double prime. Don't agree? But when the author likes to use the letter S for position. So if I called this position P, I did PVA. If I called it position S of T, what would velocity be?
S of prime.
S prime of T is velocity. What's acceleration?
S double prime.
There you go. Y'all agree? Yeah, we won't do jerk. We won't do jerk, which is third derivative. Rate of change of acceleration with respect to time. So when I'm in 3.7, we'll do a couple of these. These are fun. You know, throw a rock, stuff like that. Woohoo! I'm going to start with number 1 on page 233. I don't often do number 1, but it's a good one. Here's the function. And when FT.
Is this related rates?
What's that? Yeah. Oh, no. Good question. Related rates. I want 2 days for it.
Okay. Yeah.
So today we'll wrap up today. We'll wrap up 3.7. I mean, I'll get your questions tomorrow. But you know what that gives us? That gives us Wednesday and Thursday to really make sure you know this last section called related rates. Is it hard, Doris? No, but every circumstance changes. You know, volume of a what? Cylinder, volume of a cone, volume of a box, area of a box, and all this stuff. And you try to deal with related triangles and how fast things change. But this stuff, you won't find nearly much, you won't find it as challenging. And it's kind of fun. We just need to know that, right?
Yeah.
All right, good. They've got t cubed minus 12t squared plus 36t. First question. All right. When could you find the velocity? Oh, and I should mention this. I'm sorry. I won't run the board. F of t does represent the position of a particle. All right? The position of a particle. A particle moves according to the law of motion. S equal to F of t. T is greater than or equal to 0, by the way, everyone. T is greater than or equal to 0. T is measured in seconds and F is in feet. Okay? T is greater than or equal to 0. T is measured in seconds. S is in feet. What do you all get for velocity?
3t square minus 24t plus 36.
Does this section look tough?
No.
Good. That's what I meant. So Melraj, we'll spend 2 days on related rates, because is that hard?
No, no.
Good,
really.
but hey, let's keep going. I had a bunch of A, B, C, D, E's here, okay? The next question. Now, if you have to, use your calculator, I don't think you'll need it, but if you have to. Could you sketch the velocity graph? Could you sketch this velocity function you just brought up?
Yes.
And feel free to call this velocity function v of t. Now, does anybody know what the shape of this would look like?
3t squared.
Austin, it's got a t squared, it's probably what? Like this? But a lot of you may pull out your calculator to graph this, right? You can. But if you're like me, I'm like, I don't feel like going to get my I got chalk on my hands, I'd have to what? Get chalk on my bag, so I'm just thinking I'm gonna find the x-intercepts. So how can I find the x-intercepts of this? I was thinking I could just factor that. Now wait, can I factor this, dude? Let's just see. I can factor out of 3, what would I be left with? T squared minus 8t plus how many times 3 on 36?
12.
Now, can you help me factor this so I can know where the x-intercepts are? Here's time. These x-intercepts on this axis. Two numbers that multiply to 12 add up to -8. -2 and -6? I know where this parabola's sitting here. I didn't even have to get out my calculator. It hits at 2, where else? There it goes. Hey, what was it when it was 0?
36.
Yeah, I just didn't feel like getting on my calculator. So it was up at here, 36. Then it came to 2. Halfway between 2 and 6, it got to its what? Lowest point, you agree? 6, because of symmetry. You all agree? Now, if you want, you could remember, wait, what's negative b over 2a? Do you remember that in pre-calc? They always made you do negative b over 2a for a vertex. Don't worry if you forgot that.
Negative
It's a
b-
formula for finding the vertex of a parabola.
Yeah,
Negative, that's b and that's a.
2a, yep.
If you want to put it down, Kelly, negative b over 2a will give you the x value of the vertex. And you'll notice, what's negative 24 over 2 times 3?
6.
4.
4.
So at x equal to 4,